Let's look at the fundamental theorem of calculus part 2. Before we do the before I introduce this part 2, let's look at the one example, which is the integral of 0 to x, and here is t squared dt. Okay, so here this means this integration variable is t, okay, not x anymore. So the antiderivative for the t squared is t cubed over 3, right? If you don't believe it, you can just take the derivative for this term, then you will see it will recover t squared. Then we evaluate at 0 and x. So it would be x cubed over 3 minus 0 cubed over 3. So this is x cubed over 3. So this would be a function of x, right? So you can see for the different value of x, you will have the different result, right? So this would be a function of x. If the integration limit is not a constant anymore, which is a variable. But be careful, here we have never have this kind of things. The integration variable cannot be the same variable in the integral limit. This one we never have. They must have the different variables, okay? So you should be careful. So if this is a function of x, so we can always take the derivative, right? So now let's look at the derivative of this f(x). So which is the derivative of x cubed over 3. You take the derivative, it would be x squared. Okay, so you see the result, and this here, this is the integrand, right? This is the result. If you have this integral, you take the derivative. The derivative of t squared dt, you take the derivative. It's equal to, we just do the calculation, it's equal to x squared. So you see, we just plug in x into the integrand t squared. Then you will get your result. This is called the fundamental theorem of calculus part 2, which says if this is the fundamental theorem of calculus part 2. It says, of course, we assume this function should be continuous, okay? And it says if you have the integral from a to x, f of t dt, you see, I will not write down f of x dx because here we use x, here we must use a different letter t. This one, you can imagine at last this would be a function of x, right? So we can take the derivative of this function about x. It would be just plugging x into the integrand. Okay, so this is the part 2. Let's look at some remarks for this theorem. The first one, the integral from a to b of f of t dt. This is a number, right? This is a definite integral, which will represent the signed area from a to b. And this one, integral from a to x, f of t dt. This is the capital F, which is a function of x. Okay, a function of x. See, a function of x. So now let's look at the geometric meaning for this function. This function is also called an area function. So if we have this curve y equals f of t, and this is the t-axis, and here is a. If x is here, then this integral would be the signed area for this region, right? If x is here, this integral would be this region, this. So you see, as x at the different position, you will have the different signed area, right? So it's called, the area is different, so it's called an area function. So this is the first remark. The second remark, if here is the upper limit is not a x, is an expression of x. What is the derivative? Right, this is the derivative about x. What is the derivative? So I will skip the derivation. I will tell you the result, which is equal to, you plug in u into f, so replace t with u of x, then multiply by the derivative of u. So this, the derivation is actually using the chain rule, you will get this result. For example, if you have the derivative, which is 1 to x squared of sine x cubed, t cubed, sorry. So you see, we cannot write the same letter, t cubed dt. So we want to find the derivative of this function. And the first thing, it's not easy to evaluate this definite integral. Then you take the derivative. It's impossible to evaluate. But with this fundamental theorem part 2, we use this formula, right? We just plug in, so here is a constant, here is a function about x, here is x squared. So we just plug in, replace t with x squared. So x squared, then cube, right? Then multiply by the derivative of x squared. So this would be sine x to the 6 times 2x. So you see, even the integration is very complicated. But if we want to take the derivative, it's a very quick way to get your result without evaluate your integral. Let's look at the third one. Let's do the more extension for this formula. If the integral here is v of x, the lower limit is a function of x. The upper limit is also a function of x, f of t dt. What is the derivative about x for this function? It's very similar. So the first thing, we need to plug in the upper limit. We plug in the upper limit, then multiply by the derivative of upper limit, minus plug in the lower limit, times the derivative of the lower limit. So you see, this one is, the second remark is just a special case of the third remark. Why? Here, the second remark, here is a. Here is v of x. If we take v of x equals a constant of a, then you will see the derivative would be 0. Sorry, here is x. The derivative, if this is a constant, the derivative would be 0, so you have no second term, it would be the first term. Right? We will recover the second remark, right? So this formula is very important. You just need to memorize this formula, then you can do everything you want. So let's look at some examples. 0x e to the t squared dt. We want to find the derivative about x for this function. So it's equal to, we plug in x squared, right? Then times the derivative of x, minus, we plug in 0, times the derivative of 0, right? We just use the second remark. So this would be e to the x squared minus 0, right? So this is actually the fundamental theorem part 2, right? We plug in x directly. Here is just x, not an expression about x. Right? So that means the fundamental theorem part 2 is also a special case of the remark 3. Let's look at more complicated example. Here is x squared. Here is x. Here is x plus 2. So here is sine x squared dx. So we use the formula. We plug in x plus 2 first. Sine of x plus 2 squared, right? This is the inside sign, times the derivative of x plus 2. Minus, plug in x, sorry, here again, I made some mistakes. Here should be what? T squared dt. Don't make this kind of silly mistakes, okay? So it's sine of x, replace t with x squared, so x squared squared times the derivative of x squared. So if you do the simplification, it would be this one, this times 1, right? Minus sine x to the fourth times 2x. This would be your result.